Yes, hello. So, let's get on with this session. We were talking about regression in the last classes, uh, you know, and today we're gonna be doing classification. Specifically, logistic regression is what we are trying to do. Okay, just to recap what we did from the last class, get on the same page. Sorry for the mess here. Yeah, so I was talking about simple linear regression last time. All we did was create a model using PyTorch for a single neuron with a single output coming in. Um, few things are happening here. Basically, multiplying it with weights and biases and getting an output. And we created few helper functions, you may call it, right? Um, from a few versions of our models and functionalize them a little bit. That's what we did from the last session. And today we're going to do classification. So what is classification task? So regression task is a one in which you have mostly the labels is where it differs, right? So label is continuous in regression. Okay, what it means is, let's say the a very famous example of house pricing. The pricing of houses can be uh, $1,000, or like in the scale of 100,000, 200,000, 1,000,000. So it's continuous, right? That is what we call continuous labels. So that would be one of the examples of regression. But in classification, what we have is classification is we have to classify between two things. Maybe you have to classify it's a dog and it's a cat, or someone has a particular disease. Maybe someone has cancer or not cancer. You know, so that's what we call a classification task. So it can be a binary classification, which is just like 1 and 0, yes and no, yes/no. So you're trying to predict, does a person has a cancer or not cancer, so yes and no. So we label it as 1 and 0. So there are, then comes multi-class and multi-labels. Also multi-class is where you have multiple classes, so you want to classify between a bunch of animals, a hen and a cock and a dog and a cat and elephant and all that stuff. So multi-class would be something like that. Or one famous example would come to my mind as a classification of handwritten digits. So you have 10 classes, 0 to 9, right? And you are supposed to build a model that will classify the handwritten digits. So that is multi-class. Then comes in multi-label. So this is, sorry, yeah, multi-class, and then the multi-label ones, right? Multi-label, multi-label is basically you have two, three labels associated with one single output. Um, for example, if somehow you are trying to um classify between like 1, 2, and 3. Okay, like in binary we have 0 and 1, right? So you want to classify between three different things, and you know uh, you just use one output neuron. So every time it says 1, then it means, if you remember iris data set, anyone who has done machine learning, they knows there are three type of flowers, right? Three flowers are there, and you can associate the flower A, flower 1, sorry, flower A can be you are putting in number 1, flower B can be your 2, flowers C can be your 3, something like that. And just one output is coming out, and you're predicting 1, 2, 3. And that would be something, in a sense. So that would be multi-labeled data set or classification practices. Okay, that's it. Mostly what we're going to do here is a simple uh, classification of a dummy dataset that we are creating using scikit-learn. Scikit-learn is another machine learning library, just like PyTorch is for deep learning. Most of the machine learning stuff happens in scikit-learn, right? Uh, so in classification, you can, if you have like 2D graph, okay, you're trying to have, there are two labels. Let's say the first is this guy is here, and you know, and the other one is some here like this, something like this. So what we essentially have here is a way to classify between both of them. So you want a simple line here. You might say that probably this line is doing the job. This line is doing the job. It's classifying the green dots from the brown dots, and you want this, basically. This is what we call a decision boundary. Decision boundary, right? Okay, whatever. So this is what we call decision boundary, and we are trying to find this decision boundary. In this case, you see one of them is in the wrong side, but that's okay, because in real data set you won't really find a exact difference between them. There will be some data sets that will kind of skip the line and go to the other side or something like that, right? Skip the boundary. That's okay. We are trying to estimate, we are trying to generalize our model to a general decision boundary so that we can classify between both the elements. That's what we are going to do here as well. Okay. Um, yeah, I will go through it, and if at all I feel like there is a need for a little bit mathematical explanation or something, I will try to do that on the pen and paper, right? Okay. So let's get straight to the code. Okay, I'm in the debug mode as I usually do. I have this interactive session also running here. Um, so okay, so let's start. So I have imported all the important libraries and stuff. We are gonna make a data set right now, a dummy data set, and it would look. So you have, let's see the size of make moons. Make moons is mod a function from scikit-learn, which helps you create a data set of for classification. So if you see x value and y value, let's just see it once. X value, it looks something like that. Let's see the shape of the x value. Shape is 100. There are 100 rows, and two features are there basically, right? And the y value looks something like this, 0 and 0 and 0. So this is a binary classification that we are trying to do. We are trying to predict if this uh, dude comes in into your model. I might want to predict 0 or 1, something like that. Okay, so you can also check the shape of this one. It's 100. Okay, so say a data set looks something like this. um, you know what, I'm going to delete all of them. No need for that. So data set looks like this. Hmm? 1 2 and this 3. This is your x1, this x2, and then the y. That is your features. So this whole thing is your x, and this is your, of course, the y, right? The big X, you can call it. This. Let's say this is our small x. Okay. Um, this is your data set, and there are 100 samples all the way down here. Okay. Cool. So we have split already. Actually, because we are using a scikit-learn, it's already split into x and y, so it's okay. Let's go ahead and again, we are trying to do train test splits. The size is 20. So now if I go and check the size of val or the train, whatever, shape shape is 20. So, and if I go with x train dot shape, is 80. So there are 80 now. As I said, in this big data set we have this much, right? This part is your X train, sorry, you can just say training part, right? Training part, and this part is your evaluation part or test part, whatever you want to call it. Right now we are not creating three sets. Mostly they do like they have a if this is the big data set, you have this much training data set, training, and then break this into evaluation and test data set. So while you're training, you also can do evaluation right here itself. And after the model is trained, you want to test it out using this testing data set. So that's three data set. People use them, but right now we are not using them to keep things much simpler. Okay. Yeah. Um, okay. Let's go on. With standard scaling, you know what standard scaling is? It's just scaling the whole basically I really don't think we need it here because it's almost in the same scale, but think of this, if let's say example of the house, right? This is your number of rooms and this is a square feet. You know, number of rooms would be 1 and 2 and 3, something in one digit, right? But the square feet might be 1,000 square feet, 2,000 square feet, 4,000 square feet. So you see a clear difference between the ranges of numbers. So first this guy is going from, let's say, 1 to 6, okay, and this guy is going from 2,000 to like 10,000 or something, right? So you see a clear difference between the ranges of both of them. So to kind of get them into same range, we want to scale them. So that's what we call standard scaling in a sense. uh, because what happens is, neural networks or machine learning only understand numbers. So bigger the number, it's like saying you are more important to the model. Maybe it's not that important, right? You want them to have the same importance. Number of rooms are as important as the square feet, right? If you take a real life scenario. So that's what it's essentially doing. Okay. Standard scaling, yeah. But as you can see, these guys here are almost the same scale. So but still it's okay, you can do it. So you fit it on your train, okay, and transform it. First you have to fit it on your train. You never fit your um, any kind of scaling parameters on your validation set or test set. You fit it on your train set, and then transform your train after that. Once it's fit, basically it calculates few things, that is either standard deviation and the mean, and then when you transform it, applies those formulas. Like the formula, if I'm not wrong, standard scaling formula is basically take every x and subtract the mu and divide by the standard deviation. This is what exactly is doing. So it will give it in the range of something. Uh, Standard scaling, if we have, no, it's the scale is not here. Normalizing is where we can estimate the scale, but that also we can see the scaling as well here. Wait. So once it's done, so you transform the x f. Now please have a look here. Okay, you can see the first sample or first instance from the data set, right? So just see the number 0.031 and 0.98 something, right? Now let's see x train, how it has changed. You can clearly see the number has changed and the scaling is a little different. Okay, so that's what it is. And you are also trying to transform the valuation data set, but never fit it on your uh, evaluation or testing set. There's one more function called fit transform, which you can directly use to fit on training data set and transform it. Okay, cool. Okay, let's see the figure so you can understand how the data set looks like. It's a very famous data set. Most people use it. You might find it all over the internet, to be frank. So this is what it is. So you have this generated data set. So you see the red ones and the blue ones. And what we're trying to find is, we are trying to find a line that would kind of separate them, a distributed boundary that would look something along this line. right? And this is your training data set and this is your evaluation. So you have a lot of training data set and a little for the evaluation. I mean, that's self-explanatory. Okay. Let's go in. Okay, okay, it's going to the function. Cool, cool. I should just skip it for the next time. Okay. Yeah, this is the helper function. Okay. So don't worry about that. That's done here and let's keep going. Okay. So now we are our data preparation, right? What we used to do is convert all of this. These are in arrays. These are NumPy arrays at the as of now, the xtrain, test, and xval, whatever. Now we have to convert them into tensors, right? Now you see this reshape. If you have followed the first lecture probably where we had done a lot of all the functions that PyTorch provide to manipulate your tensors, you might know what reshape is, right? So here it what it's saying. If you check the shape of y train as of now, as I have not done anything. So you see it's 80 comma. That is, it's just a single list. Single list with a, if I were to just show you also, that's better, right? So you see it's just a single list right now. But we don't want single list. We want a kind of a matrix happening, okay? Where it's there is 80 columns and one row, okay? So that's what happening here. What it's saying is I want one column and you adjust the rows as you want and I will do it for you. So -1 states that I want one column. Sorry, yeah. So yeah, if I run it right now, you can clearly see it will become 80 comma 1. 80 comma 1. So you have what? Uh, okay, oh sorry, this one, right? This one, y train tensor. Y train tensor. You see, there are 80 rows and one column as I expected. So there is one column and adjust all the data set as you want so that it fits all of them. So 80 comma 1 will be the absolutely the logical idea because there are 80 samples in that list. Okay. So now this is actually 2D. It's a 2D tensor, right? A matrix, you may call it. Now, okay. So we are also doing it for evaluation. Same thing happening for evaluation. We just did it for test. Now tensor dataset. You remember what tensor dataset does? It just creates an iterable, right? So once you do this, all you get is if I remember, you can do this next iter and train dataset, right? Too many brackets, right? Yeah. So you see this, it's coming as a batch of with x and the y. This part is the x and this part is the y. You can see it right here as well. Like if I do this, if I take the first ones from each of them, that is indexing the first ones, and you see the same values are coming in. But only difference here is we are creating a kind of a iterable. You know what iterables are, right? We can run a loop over them. So yeah. So then evaluations dataset also needs to be transformed into a tensor dataset. That's what happening here. Data loader. So here simply we take the tensor dataset that we have created and we batch them. So here the batch size is 16. From the last time it was 16, right? And we are keeping shuffle as true. So dataset will be shuffled. Okay. Yeah, cool. I don't think I need to tell you what they are. Please, if you don't know, there is a video called data sets. You can check that out to understand how things are working here. Yeah, cool. So here, actually, this is something, there are two ways to understand how logistic regression works. Okay, one important part of that is sigmoid function, and it's kind of derived from odds. So in probabilities and odds are like probabilities but a little different. We use colloquially odds in a very different way than how data scientists or statisticians uh, model them a little bit. So in so odds are pretty different from what they are. So we would say the odd of getting heads uh, in a fair coin flip are 1 to 1, since there are like 50% chance of success and 50% chance of fail. The odd will be 1:1. So that is something. I mean, this seems a little redundant. I seriously don't think this is a good way to understand logistic regression. So I am gonna skip these few parts, but I'm gonna go through the most important part about all them. That is uh, comes here, which is from logits to probability. And what it is basically sigmoid function. And what is sigmoid function? We're going to have a clear look into that. Okay. Yeah. So sigmoid function is simply, it looks something like this. Of x, let's say 1 divided by 1 plus e to power minus x. This is what sigmoid function is. And what it does is take some value of x and map it to a probability of 0 to 1, and function looks something like this. So if I were to do it properly, so this is of course your um, x values, and this is your sigmoid function value, right? Okay, this is 0. So now it asymptotically goes here, and this, yeah. So this is your 1, and so this is asymptotic towards 0 and 1. So this is your 0th point, right? um, and this is your 0.5. What it does is, now think about this: 1 2 3 4 5 6 7, no, 1 2 3 4 5 6, whatever. So whatever the x value is, what it does essentially is it maps. For example, if this is the value you got 3 and you're putting it inside this one, in the sigmoid function, it will give you this value. So the y value would be somewhere around here, so 0.81 or something. Okay. And some some uh, some dude is saying their x value is coming out to be 7 or something. It still will be here, somewhere around here. That might be 0.91 or 92 or something, right? 0.92. Assigning a probability to the x value that is coming in. That's how simple it is. So what we are trying to do is binary classification, right? You are trying to find if something is or email is scam or not. One being email is scam, sorry, spam, sorry, and 0 being not spam, right? So you want to assign a probability. Basically, what want me to problem? For example, I I will select this threshold 0.5 if I do all this calculation with x and all that stuff, and I feel and it's giving me a value of this, 7 or 2 or something, and I can clearly see that it is basically this one. It's probably a probability of 0.1 being it's a spam email. So this is your probability assigning to first one. Okay, like the one value in your binary classification system. So that is what exactly sigmoid is doing, and we will get to know more into what's happening in the whole process. Okay, cool. Sigmoid function is being activated, blah blah. Let's also, we can draw it. We can also draw this one. Okay. Okay, sorry. By the way, sigmoid is also defined as the inverse of log uh, log odds. I don't want to get into that. So here I have defined it. This is the same function that I just wrote here. This is the same function exactly. But why make it ourselves when Torch has already built it for us? So let's just do this and see once for ourselves. So you see log odds basically is the x value, whatever is going in. and then you see a function going. So at 0 it's 0.5, and it asymptotic towards 1 and 0 along the both sides of the x-axis. So infinite towards positive infinity and negative infinity along the x-axis. Okay, so that's that. um, so what we did is we created a simple. So if you want to check what would be, let's say this value. Okay, this value, if I want to check tensor sigmoid of, this is the value I'm putting in, and if I say it's 0.70, so it's assigned a value 0.75, and let's say this is assigning a value of 0.25, so something like that. Okay, you can also go into deeper into the understanding of that. That's cool. Let's get to this. Okay, logistic regression is simply what we are doing from the scratch is this. Right now, what you are going to build is, we have two inputs, so two input would come in, x1, x2. These two input will go in to one neuron with some w1 and w2, right? Let's give a proper naming, x1 and x2, with some bias. It will give out some output. Okay, this exactly linear regression. So the equation would here would be x1 omega 1 plus x2 w2 plus whatever the b is. This is your y hat. But now you see, this can be any value, right? You know the value of x1, you know value of, you will initialize a w1, w2 and w3, and it will be a value ranging from x to anything, right? It can go from and it can be a negative value, it can be a positive value, all over the places. You want probability out of it. You really want a probability, right? You want a value saying it's 1 or it's a 0. So we just found one function that helps us do that. That is use sigmoid function. What if I take this whole thing, we actually do not denote this as y hat, because y hat is mostly denoted as the what do you say, the prediction value, right? So mostly what people do is they call it z or something, or o, I'm calling it z as of now. Okay, so what they say is, take this z, do the whole thing, and why don't you put it into a sigmoid function, 1 plus e raised to the minus z. Okay, so if I were to spell it out, 1 plus e to the power minus of plus b. So if I do this, this will always be between 0 to 1. So that is your probabilities, right? Probability can only go from 0 to 1, right? I don't need to tell you that. So that is essentially what we're trying to do. Okay, cool. So once more, what happening is, inputs are coming in, they are numbers going into the whole thing. It's the same thing that we did for linear regression. Coming in, this is the function going in, one thing comes out of it, and you pass this whole thing. This whole thing is then passed into a sigmoid function. Sigmoid function outputs in this range 0 to 1. Okay, now of course, no, we need to build a loss function to do the backpropagation. All that stuff will come soon. So that is what sigmoid function is. Okay, so we are going to create the model using PyTorch. Okay, yeah, let's do this. You go in, you created a seed function, then you add a linear layer, then you add another linear layer. Let's go and see this one. What is the state of our model? This is the state of our model. So state of our model says our w1 is 0.5406 and w2 is 0.5869. Your bias is minus 1.657, something like that. So if you put all the values here, you'll get the answer, right? You have what you have this one, this one, this one. You also have, let's take any first instance of them, and you can seriously calculate with your hands as well, right? Cool. That's that. Also, if you want to see the outputs, there's something called as torch info. You can import torch info. From torch info, import uh, summary. So this is what summary looks like. Okay, what it tells you is, basically what's the model looks like. Though there's a linear layer is there. Of course, there is one linear layer. You see that this is your linear layer. This is your linear layer, right? Linear. This is your input layer. Okay. That's your hidden layer or hidden layer, what we call. Okay, this is your input layer. This is your whatever the output is coming here. Okay. Um, cool. So what it's saying is I have seen input size is 16 comma 2 because our batch is actually 16 one at once. 16 samples will go in, right? So that's why you can assign the, if you don't assign it will just take one. Okay, so that can also be done. So but if you want to see the clear picture what's happening, so they're going to be 16 is to 1. So output, it will be 16 is to 1, and the sigmoid function will also get the 16 is to 1 out of it. And here you see three parameters. Of course, there are three parameters, that is w1, w2, and b. So you see in the linear array there's parameter, but sigmoid function has no parameter, right? As sigmoid function is just there to put out the probability, spit out the probability from this function. So if you want to see, I mean, it's much more helpful when you have big models, you understand better. So you can see uh, for the 16 samples that you're giving in the first batch, you will get one output from the linear layer. That is exactly what you're getting from the linear layer. And then you put it into the sigmoid function, and you will also get this for example. So basically, it's like a matrix multiplication is happening, right? So if you take the linear layer, what is happening? You have 16 at once. 16 comma 2 is happening, and then the first layer is goes like 16 comma 1. So if you do a matmul is 16 comma 1, so that is what it's showing, that the first layer will give out this is a size, and then you put it into the function. A sigma function does not have any multiplication and stuff, it just takes it and do some simple transfer. So if you really want to see what 16 is to, I mean, I hope you saw that. So you multiply 16 is to, that is your data set, like first batch of the data set, you multiply it with this matrix, that is this matrix, right? W1 W2 kind of a thing, and you get that. Okay. uh, then you put it to the this is the output that it was show 16 is to 1 is what was showing, right? 16 is to 1 is exactly what's showing, and you put it in a sigmoid, it's also spit out 16 is to 1 only. Okay, so that's exactly what's showing here. So output at the end will be 16 is to 1. That is a big array of a 2D matrix with 16 rows with some numbers, right? Some numbers are there like this. So this is your output. So there were 16 instances in one batch. You remember 16 instances in one batch, x1, x2, and all that numbers comes in. So every single instance will be mapped to one of these instances, right? So that is what is happening. Okay, just so a few note on sigmoid function is that sigmoid function is called what we call in machine learning as an activation function. So it not just spits out probability, that's one of its functions, of course, but it also introduces non-linearity in your models. What happens is uh, few models, they any, let's say the regression model, it will always create a straight line no matter what, right? But to have, but your data set, for example, this data set that we already have, right? If we know for a fact not a single straight line will actually classify them, and here it won't classify them perfectly, it is put a straight line like this, no way, there's no way I can create one single line that will absolutely what do you say, define this or classify this. Hmm? So what you really need is, you can see might be a kind of this kind of a flow is happening, you see that it's a curves happening. So to introduce these curves into your model, you need activation functions. So introducing non-linearity. So sigmoid function is non-linear. It can be used to map logits into probabilities. What are logits, you might ask? Logits are simply this the z value is your logit value. So whatever your model spits out, that we call as your, it's called a feed forward layer, feed forward network, you'll find this word all over the place in the research papers and all that stuff, right? So whatever they spits out, they are called as logits. Okay, so what we have sigmoid function is doing, taking this logit, that is your z value, and putting it into a probability, right? Okay, non-linearity, the non-linear function play a fundamental role in neural networks, and that is adding non-linearity to your models using activation function. So sigmoid is one such activation function. There are other activation functions as well, like ReLU and TANH, and variations of ReLUs are there, like CLU, parametric ReLU, and ELU, and all that pretty cool stuff, right? So sigmoid is one interesting fact is the sigmoid is the biological inspired and first activation function to be used back in the old days. It was followed by TANH, and more recently we have the ReLU, and the whole family of activation functions of ReLU is there. Okay. However, there could be no neural network without a non-linear function. Have you ever wondered what would happen to a neural function no matter how many layers deep if its activation functions were removed? So what happens is, in when you build a new big linear sorry big neural network, a deep neural network, without activation function, it, no matter what, how many layers you add in, it will always be a linear function. That is, it will always create a linear line. Okay, that's it. Basically it will be just be a linear regression. Okay, one thing more, let's see the notations of this a little bit, so that, okay, so right now, people, we can denote this weights into a big w matrix or vector, whatever you call it. uh, so it can be like b blue1 and w2 in this case. Okay, and the x would be something like this: 1 x1 x2. Okay, why we add 1 is, I'll tell you. Okay. So z that we are trying to find, the logit function, right? Logit function is nothing but take the w transpose and do this. I've actually shown you this before, as I suppose. So when you say, there's a way of writing, as you can see, this is what we call a column matrix, or column vector. It won't work call a vector, actually it's a column matrix, right? So you transpose it, it becomes a row matrix like this. So it's w t. This is how people denote it, and the other one would be like 1x1 x2. Okay, now you can do dot product between them, right? So if I take x w1 w2 and do the dot product, right? x1 x2, you can clearly do the dot product. That is b plus omega 1 x1 plus omega 2 x2. Isn't this exactly the z value? So what we essentially did, we created a simple representation, that is x, uh, this representation for the whole thing. This whole thing can be represented as this one. So most of the papers you will find, or classes or online, I think MIT's, Stanford's machine learning lectures on all that stuff, you will always find this kind of notation, and this is what exactly is happening. Okay, cool. Yeah, let's go on with our model. So we created a model. Models is as a linear layer with two inputs, one output. Output is sent to the sigmoid to get the probability. So converting logits to probabilities. Logits, I just told you, right? Cool. Let's move on. Okay. Now let's see what loss function do we really use. Like in the linear regression, we had a very simple loss function that we used, that was uh, mean square error, right? Mean square error value was pretty simple to derive, but here we use something called as cross entropy, and it sounds a little scary, but it's really not. So we're just testing few things. Okay, so we already know, we already have a model, and now we need to define a parameter loss for it, that is for a binary classification. For this, we use something called as binary cross entropy loss, sometimes known as log loss. Okay, so there it's denoted at BCE. You will find the function also as BCE. You might see right here BCE loss. It's right from the PyTorch implementation. Okay. So what it requires is, it requires a predicted probability that comes from your model as returned by the sigmoid function, right? And the true value, whatever the true value was for that. When you're training, you have true values, right? You have the labels, and your model also predicts out something. So you do a difference between them. When we were doing a regression, here it's a little different. Okay. For each data point I in the training set, it starts by computing the error corresponding to the point's true class. Okay, we will get to see what that is soon. Okay. um cool. Yeah. Let's do this. There are two ways to go about it, actually. I can show you a few ways to go about this. Okay. Firstly, what it does is, if the data point belong to positive class, we would like our model to predict a probability close to 1, right? If there is a data set, now this first data set from a data set x1 x2, this first one, the label is 1. So we want our model also to spit out a probability that is close to 1, right? So it's close to 1, so 0.8, 0.91, something like that. Okay. So that is the essential idea we are trying to see for ourselves. So a perfect one would result in a logarithm of 1, which is 0. It makes sense. A perfect prediction means 0 loss, right? So if it were, if yi is 1, then the error would be what? Log of 1, which is equal to 0. So if the actual data set says that it's 1, and your data set is also saying that it's 1 or close to 1, then you know for a fact that the loss is 0. Okay, cool. So what if the data point belongs to the negative class, you might ask, right? So then we cannot simply use the predictor probability. Okay, because the model outputs the probability of a point belonging to the positive, not the negative. That is what I was saying. So you remember this function here. So what it does is, it always spits out the probability. This is 0.8. If something is here, it's 0.4, right? So what it says is, it has 40% of chance, 40% chance that it belongs to class 1. This says it's 80% of chance belongs to class 1. It does not spit out the probability for the negative one. It spits out the probability of only the one class. Okay, cool. Okay, so because the model outputs the probability of the point belonging to positive or negative class, likely the later can be easily computed. Because if, let's say, the probability of yi is equal to 0, it's simply what? 1 minus probability of yi minus 1, that is equal to 1. That's how simple it is. Probability of something being 0 is what? 1 minus the probability of something being 1. Simple. Probability ka rule, right? Cool. Thus, the error associated with the data point belongs to negative class is simply what? Simply the error if yi is 0. The error for that class would be log of 1 minus probability of yi being 1, right? What is the probability of class being 1? I want to minus it that, then take the log of that. So that will be the error. So, okay. Once all errors are computed, then we aggregate them. Okay. So what we do is, we create something like this. This is what we call a binary cross entropy. BCE 1 minus. You will understand why the minus comes in soon, actually. Okay, so I will give a much easier explanation of this one once we are done with uh, this whole thing. There are, as I said, there are two ways to go about it, right? What is the probability of yi being 1, and plus summation of log of what is the probability of yi being actually 0, so it's 1 minus 0. Okay, I hope that makes sense. So this summation is going from I to 1 to all the positive values. This is going I to 1 to all negative values. So you see number of positive and number of negative, that is total number of samples. So in the training set, it will be equal to 80 itself, right? Cool. That is one way to go about it. Okay. And so that's what we are trying to do here. Okay. Check this out. We are creating a dummy label that is 1 and 0. So the first label is 1 and the second label is 0. Okay. And my predicted label is, let's say, 0.9 and 0.2. So it's pretty good, right? I'm predicting it's the model, it's probably 0.9 percentage the class is belonging to 1, and saying 0.2 percentage is belonging to 1, that is, yeah, it's 0, right? That makes sense. I hope you can relate to that. And okay, let's then we move on to the next part. Is we are creating the positive prediction. So just so you know what I'm doing here is, dummy equals to 1 means it returns a true value for the part in the list where it's actually true. If I say dummy equals to true, so you see dummy labels, which was this label, where is it 1? It's 1 at the first index, right? That's what I'm doing. And all I can do is take that label, this dummy prediction, and put it back here, and you see 0.9. So I'm just getting the prediction for the one that was giving a positive value. So the positive value or the one value, you know, is 0.9. My model is predicting 0.9. Okay. Yeah. So first summation is simply we are taking the log of the prediction and doing it. So what I can do is show you one by one like this. What's happening here is we are taking the log of this, and you see the log as we got the log as is just one. And essentially we have a batch, so there are n number of, let's say in this 16 of them, right? So you add them, but here is just one, so the sum will also be the same, right? But still I just want to show this. Okay, sum being that you got the sum out of it. So one thing you noticed, this is a list now, but this is just a tensor now once you do the sum, because it's an aggregation, right? Aggregation function is there, sum is an aggregate function. Okay, cool. So for the negative class, do the same thing. Find where in the index did you find the label to be 0, and let's see what is the prediction. What is the predicted value? Negative prediction. What is my prediction? Okay, and you do the same thing. Take the log of 1 minus negative loss and see what's so if I go and hover over it, you can still see that is 0.2231. Yeah. Okay. So now the total loss, that is the, we are trying to find the what do you say, the denominator part here. In this, you see the denominator part, number of positive and number of negative. That is exactly what you're doing. So if you do this, you will see the size of this one, that is 2. So you will find it 2. So total number is 2. Okay. And now we do the same thing here. First summation, second summation. If you see the equation also, like the first summation is this one, right? Take the log of everyone that is positive. Oh, that is what we did. Log of everyone that is positive and sum it up. That is what we did here. Yeah, I mean, this is very helpful in the sense you need to know how to convert a mathematical equation into a Python function. You can use ChatGPT. There are so many tools right now. I mean, it's very easy. I can just take a screenshot of this whole function and put it in ChatGPT and ask him to spit out a code in Python for the mathematical function. Okay, but yeah, it's a good thing to visualize it in code, and if you can see it in code, you should also be able to visualize it in text. If you are coming from a mathematical background, it will be much easier for you to understand. But if you are coming from a code background, then this might be much easier for you to understand. Yeah. Cool. So what you see is this first part, the first summation is coming from this part. The second summation is coming from this part right here. Okay. And then you divide it by the n total and you add a negative. Why you add a negative is simply because of the type of function the log is. If you see the function of log, like how the graph looks, this is what a log graph looks like. It cuts 1, here it's the 1, and it goes to the infinity. Okay, so there log of negative do not exist. I mean, that's a whole history behind it, right? Um, so this is what a log looks like. Okay. So anything that is between 0 to 1, you see, 0 to 1 will always have a negative value. Okay. You don't want your errors to be negative values. So what you do is just add a whatever is gonna come out of this one. It will always be a negative value anyways. So let's just put a negative outside. So we so that it becomes positive. So this is what we call a negative log or something. Okay. So that's why we put the negative here and in the equation as well here. Here we put a negative here, right here. Cool. Let's go on. Calculate the loss. Let's print out the loss as well. Loss is 0.163. Please keep that in note. It's gonna be helpful in the what we are gonna do next. Okay, you calculate the loss. Now this is just a complete implementation of this whole function. Exactly. Instead of doing it one by one, we all did it once. That is, sum up the labels into this whole thing and then add it with 1 minus the dummy label, whatever that is, and then the whole thing. So you will see the same thing is happening here. Check it out. If I run this right now and again check the loss, same value comes in. Cool. That is that. I hope I didn't miss out on anything. Okay. Okay. So this above formula is what we see, a very clever way of computing loss in a simple expression. But the split of positive and negative point is less obvious. If you pause for a minute, you will realize that the point in the positive class, that is y equals to 1, have their second term equals 0, while points in the negative class, y equals 0, has the first term equals to 0. So now what is this all about? So if I were to put all this thing into one really cool formula that we are gonna do here is I'm gonna spell out this whole thing, this formula. Okay. uh, See for yourself. Okay, the actual BCE formula for any y is this 1 by n, that is total number of data sets. Then I goes from 1 to n, that is total number of data sets. And this is where the magic happens, is y of I log of p probability of yi being 1, and you add the second term, that is 1 minus y of I, then log of probability of y, sorry, this would be a negative, right? So 1 minus probability of yi being 1. Okay, let's dumb it down even more. Simple terms. Let's take this whole thing. This whole thing, probability of y being 1 is what? Your output from your model, right? Y hat. Let's call it y hat. So you can just put y1 by n summation of I equals to 1 to n and yi log of y hat of that high, okay, plus 1 minus yi, again the log of 1 minus yi hat. I hope this makes sense. Hope you can see this. Just have a careful look at it. I'll give a small example to really make you understand what's happening here. Let's say one instance for my data set, this instance had the label 1. Okay, I'm gonna really need a calculator at this point. If your model states that it's 0.88 is the value you're getting. So what you're this is your y dash. Okay, so let's just put it here. Give me a second. Okay, sorry for that. Back to this. So let's say our model spits out that 0.88 is my y hat. That's the probability that it's being in the one, and we know it's one from the data set. So what you do is you put this into the equation. So one by one, of course, there's only one data set as of now. Let's do summation of 1 to 1. That is, we don't need it really. So y of I. What is y of I here in this case? Y of I is 1, the actual prediction, right? The log of 0.88 is another thing that you need. Cool. And you can see plus 1 minus what is 1? 1. So this whole term will become 0. Okay, that is first cool part. Let's say the another scenario is there. Another scenario is being that there's another data point which says that the label is 0, and it states model is saying y hat is saying it's 0.2%. Cool. It's pretty good, right? And if I put this also into the whole thing, so minus 1 by 1, of course, then what is this value I had? It's 0. Then this part becomes 0, but this part will be 1 minus 0, that is 1. And log of, what is this? 1 minus 0.2, right? Right. And so here essentially what we have is log of 0.8. Okay. So now if I were to, so you see one thing, this one equation is handling both positive and negative. So every time you get a positive value, this part will become 0. If every time you get a negative value, this part will become 0 automatically. And now let's also see one more thing. That is, let's see this only for this example. That is your positive example. The first example we said this whole thing will become basically minus of log of 0.88, right? Let's say your model says we know your model says the output was supposed to be said is 0.3 or something. If it was 0.3, the whole thing will just become 0.3 here. But see the values for them. Okay, check out the values. uh, if I do log of 0.88, that is, if I do all with minus of minus 0.55, okay, which is basically 0.55. Okay, now here what we can do, one more thing, 0.3 is there, so it's 0 point, okay, so 0.52. Am I taking it wrong? Yeah, 0.52. I'm sorry, one major mistake I did. 0.5, 0.88 is 0.05. That's why. Okay, 0.05, and so this whole thing becomes 0.05. So what you see clearly is, what is this? This is literally the loss. This is also the loss. This loss is for a model that says the probability of that instance, which was the true value is 1, and my model says it's 0.88. The loss I'm getting here is 0.05. But this, in this scenario, y is 1, but my model says is 0.03, and the loss I'm getting is 0.52. So what does it really mean is, when you have probability that is close to the original one, that is, it's a good model, then the loss is way less, right? That is what we are trying to do. Loss is what? A quantification of errors, a quantification of the deviation of your predicted and your original sample. Yeah. So in this scenario where you see clearly there's a big difference between both of them, then your loss value is way higher. So this is how really uh, binary cross entropy really works. I hope that makes sense. So now, uh, of course, PyTorch has a way to do this very simply. Okay, so you saw that, right? You created a function like this. If you see, actually, we were what we are doing this thing. You see this one, this was nothing but the total sum of all samples that are there, and this thing and this thing, we kind of made it into one whole thing. Okay, so keep in mind this one function, that is the function that you will use to understand binary cross entropy. Hmm? By the way, it's binary cross entropy. There is another thing called as cross entropy, which is used for multi-class classification. It's a general what do you say, equation, that binary cross entropy is kind of derived from it for two classes. Okay, that's it. Let's go on. Yeah, cool. Let's see now PyTorch function. We are using reduction equals to mean. This is basically saying that I want that 1 divided by n what do you say, uh, term in front of my loss functions. There, that's why we use mean, or we can also use it without the mean also. So I think there are three functions that it has. The first function is mean, then there is sum, and there is none. That's also there. So the default mean, so this is your default function, which is also the function that we use in our equation. Okay, sum will return the sum of the errors simply if we are just using. So if you see, the reduction has three functions. I don't know if you can see that here now. Okay, I can just click here. Okay, so reduction, see, reduction has three function, that is your none, that is your and mean and sum. So your default is mean, but you can use these two. So if you just do sum, what it does, it does not take the 1 by n factor in the equation. It just gives out the sum of all them, which basically takes out this factor, this term from the equation, and just gives out this whole sum. It's a big summation, right? And none is basically, none correspond to unreduced form, that is, it returns the full array of what do you say, full array of errors in a sense. Okay, you can also read here as well. No reduction will be applied. See, no reductions will be applied. It will give an array of errors of every single item. There's 16 of them, 16 different items will come out of it. So if you want to use them, I don't know when you use them, but okay. So again, it's a function. Nothing's there to see. It's a, as I said, it's a higher order function. It's a function. So this is a function that returns another function. So this is also a callable, and we can pass some parameters to it. Now, also we are taking in the dummy dataset from this top, right? Same dataset that we have. Dataset, not really. It's a example. So now there are two ways to do it properly. Okay. One way is, you always should pass in the prediction value first and then the actual values. If you do the other way around, it will give out a wrong answer. For example, if I do this one, it will show the right loss. That is exactly the loss we were trying to find. But if you do this, you will find the wrong loss, and wrong loss is right here, 15. Okay, so make sure always pass in the prediction first, then your actual labels. Okay, one more thing about BCE loss, that is this loss, the function that we have here, is they also have a term called weight, that is mostly none, meaning every data point has equal weight. It needs to be a tensor with equal size of number of elements in the mini batch, represent the weights assigned to each element in a batch. In other words, this argument allows to assign different weights to each element. So the first element would have a given weight, the second element would have a different weight, and regardless of the actual class of that particular data point. Okay, so I know it sounds weird. I mean, it's, you might think it's used in what do you say, imbalanced data set to give weights to the lower represented classes, but it's not used in that way. We will not get into it. um, yeah, that's that. Now let's see one more function, the one more brother of basically this BCE loss, that is BCE loss with logit losses. What it really does is, here, if you see in our model, we had to put in the sigmoid, right? But and then we have to put in the BCE, and it did all thing. But what this function does is, BCE with logit loss is, we don't need the model, do not need uh, uh, you mean the sigmoid function is not needed. You can straight away put in the logits, and it already has a sigmoid function inside it. It will do the calculation for you. That's how simple it is. Okay, cool. So the BCE loss function took probabilities as an argument together with the labels. Okay, of course, that's what we did here, right? We took the probabilities and the actual labels, right? This loss function, that is the BCE with logit loss, takes logits as arguments instead of probabilities. Okay, it means you should not add a sigmoid at the last layer of your model when using this loss function. The loss combined with the uh, sigmoid layer and the former binary cross entropy loss into one. So instead of having sigmoid at the end of your neural network, what you do is just take this, that z value, right? You remember z value, just take it and pass it, because BCE with logit loss already has a sigmoid inside it. Okay, so you must use the right combination of models and loss function. Option one is that you add in that nn dot sigmoid as a last layer, meaning that your model predicts the probability combined with the BCE loss. Cool. Second option is no sigmoid at the last layer, meaning your model is predicting logits, and then you combine it with BCE with loss function, this function. That is what we are talking about. Okay. So that is mixing this NN with sigmoid and then BCE with logit loss is just wrong. Okay. So we will see an example of that. Coming here, uh, we're basically taking in the logits for the one and one, because if you pass into the model has a sigmoid, that's why you cannot do that. But what you can do is we can take in the logits, right? So just did the logits, and in this scenario, dummy logits are like this. You see both the logits are there, and you pass the dummy logits and the actual labels, and again it spits out a loss. A loss is right here, same loss that you see. Cool. Yeah, uh, that is the difference between um, a BCE loss with logit loss and the other one. Cool. Okay, what if you have imbalanced data? I mean, this is a much deeper topic, but what you can do is you can assign kind of a weights to this thing. Before that, I would also like to tell you about BCE with logits and few of the parameters that is that. It has the same reduction parameters, that is this mean, none, sum and none, and it also has weights. It works exactly as the BCE ones, and it also has this pos weights. What is that is the weights of the positive sample. It must be a tensor with the length equal to the number of elements associated with the data points. Okay, and why is it used to? Basically, it's used for any kind of what do you say, imbalanced data set. Cool. You know what? I'm gonna skip this part for now. We are gonna straight away create our model. Okay, it's not very important as such. So model configuration, let's go through this. Let's come straight to here. Okay, done. Yeah, let's go on. Create a regularization, sorry, learning rate. Seeding model is a sequential model with just linear. We are not adding the sigmoid function because we're going to use BCE with logit loss. We are knowing, we are telling what kind of optimizer you need to do. Then we are also, it's loading. Okay, let it load. Okay, done. Defining BCE with logit loss. Now let's start the training part. Okay, we created this whole system, right, step by step, method to do model training and all that stuff, right? But we will try to go through it once, you are assigned the model, the loss functions and all that. By the way, this is tensor board something, so it's basically it's used for monitoring and seeing your losses and all that. You're putting the model into your device. These all are none as of now. Loss function, you assign them. Total is whatever. Make training, perform the training. It's spitting out this validation. It's getting all the necessary parts into it. Okay. Now we set loader. You can take the set loader, and this is your loader. That is your data set loader coming from there, right? The batches of 16, 16, if you remember. Put it here, put it here, setting the loaders. Let's go to training. Training starts right here. You set the seeds if you want, and go to the epochs one by one. The first batch is data validated. Mini batch has been created. Done. Now putting into device. Mini batch step. This is where actual training happens. The had been calculated, the loss calculated. We say the backward, that is computation of the gradients. Update the weights, empty the gradient accumulation, return the loss. So happens with all of them. Again, it's the same thing. I have shown it way before, so I'm not gonna continue with this. I'm just gonna hit this so that all the training is done. So right now the training is done. Now let's see one thing that is a very important part of this all. Let's also see the model.status as of now. Models 1. Is it model 1 or model this model, right? Okay. You can see this is the states of a model. But what I was to show is also diagram actually. I'm gonna pass this here. It will take a little time. Okay. What I can do is I can take this whole thing and run it once. All the graphs and all. It will take a little time. You can make predictions or making predictions, making probabilities and all that stuff. Yeah. This is the loss function. Now, if you see something happening here, that is validation loss is lower than training loss. Somehow, our validation has a better performance than your training. That shouldn't happen, right? Mostly what happens is in any models, you have overfitting problem. That is, it works really good on your training data, so its loss goes way down, and your testing data will have loss a little higher or above the uh, training loss. But in the scenario, you see the opposite of that. This happens because there are few different reasons, but one simple reason is actually check out the data set. Here you can actually see there are a lot of intermingling of those red and blue dots, right? They are in each other's territory, if you may say, right? But in the validation set, they aren't. Really, you can create a line here, let's say this one line, and it will almost segregate all of them with just one or two errors. But any line you draw here, it will always have few more data set. They are in the wrong territory, wrong decision, in the wrong side of the decision boundary. So that is one of the reasons. I guess that is the reason for such behavior. It happens sometimes when your data is very small and you're working on a very dummy kind of a data set. But in real life, it rarely happens, and I mean, if it happens, that's really something wrong with your model. Either you might even have just did a thing where uh, you labeled it wrong, right? So that can also happen. Cool. Print out. So if you want to make, so this is your model, right? Training is done. We can do a prediction on it. Take any four of them and let's do the prediction. So if you see what is the prediction for the first four samples, prediction is right here. Predictions. it throws out logits. The logits are being given by your model. Let's go ahead and see. If I put into sigmoid, what it gets, it will give me, it will throw out probabilities. It will throw out probabilities for all of them. Now I set a threshold. If I set a threshold here, I'm setting a threshold, and if I see the classes for all of them, so the threshold is 0.5. If you think about it, here they are using prediction, but you can use the same thing as like this also, probability here 0.5. This will also do the same thing. Okay, classes will be 111. So first it says that from the data set, the first instance is 1, second instance is 1, third instance is 1. You know what, let's just have a look into that. Maybe uh, sorry, yes, 1110. Yes, so you see our model has actually predicted perfectly, right? That's pretty cool. And that's it. There are a few more figures. If you want to see the decision boundary, I can plot it here, right? uh, Go, taking the model and the model devices x train, y train, and it's plotting the graph for you. uh, this one graph is able to tell you what exactly is happening, right? So this is the data set. This is how they are, the territory is going on. This is your decision boundary. This one is your decision boundary in 2D graph. This is, by the way, this is a logit x and y, and you are creating the this x1 x2, and same thing but in 3D. So this is your probability 0 to 1. Okay, so these guys have, the red one is your lower probability, that this has a low probability of being blue. Okay, and blue one, it says this is a higher probability of being blue. That's it. And this is like a contour plot. Okay, you can think of as a contour plot. Yeah, so that's that. Cool. Same goes for this one. Yeah. Okay, same goes with this one. Nothing special here. You see, by the way, do you see the difference in them? So you can clearly see a lot of them are being misplaced. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 are being misplaced, right? They're in the wrong side of boundary. Here, only 1, 2, 3 of them are in the wrong side of boundary. That's why you get such crazy loss functions. Loss function in this scenario, the training loss or the testing loss were doing better than the training loss. I mean, there are a few other things like the parameters that you need to train and all that stuff. So we will go into that maybe in the next class. Uh, yeah, confusion matrix. So now we are going into the area of evaluating models, or especially the classification models. Like the regression model really did not had a lot of evaluation. There are like R2 square and all that, adjusted R2 square. Nothing crazy there, to be frank. But here in classification we have things called what kind of threshold value you want in your sigmoid function, right? There was a threshold value I gave here 0.5. What kind of threshold, how can you estimate this threshold value? We use ROC curves for that, and in what scenarios you want this to be higher, what scenarios you want to be lower. There is accuracy, there is precision and recall, sensitivity, specificity, true false value rate, true value rate, you know and all that small things we will see in the coming up sessions. Okay, thank you for joining in. Tata.